Testing. Okay. Hi. So I'm Edmund, and talk is mainly an introduction to statistical learning theory. Very high level and a very timeline. And so there is a little bit. I plan it for most of the audiences. There are people who are experts in machine learning and statistical learning. So for those of you, some of the things in here are going to be elementary and literally statistics 101. But it's open to synchronize convention and synchronize notation and like that. And there is another element to this, which is the geometry element. So this is theory, and this part of the talk will be phenomenally, right? Would gesture to we are going to be, but not yet. Okay. Just a quick rundown on the low run. So I think Dan introduced most of it already.
Hey, Edmund.
So the introduction to the statistical learning theory, this SLT low one, and then we will go to the actual geometry side of things and look at the effects on geometry. Audio problems. Testing. Testing 1, 2, 3, 3. Testing. Testing. 2 is a prime. Testing 1, 2, 3. Okay. Testing 1, 2, 3. Testing 1, 2, 3. 2, 3, 5. Should I speak louder? Is that a problem?
Audio is truly lag.
So just ask, is it audio problem or a lag problem? The volume. Did I touch something here? Oh, it's repeating. Hello? Testing.
Let's try this. Because I just changed the device.
Testing 1, 2, 3. Okay.
Okay, no problem so far. Let's try this. Okay.
Oh, using this one.
The one.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 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 I should say out front, thank you, Jesse, and thank you to all the organizer for getting us here and having all the equipment for this. Thanks. Okay, so the ultimate the ultimate goal of this low road, SLT low road, is to get at this free energy formula to get us kind of a same not a full complete proof, but sort of seeing the main features and sketch of the proofs. And the main references are the what we call the gray and green book. Here they are, those are the covers by Watanabe. Okay, so done this. So lots of background materials, but mostly notations and conventions that machine learning experts will be familiar with. I won't go into details all the way down to, say, measure theory and things like that. So take a charitable interpretation of everything I put on screen. So if things need to be smooth, they are smooth. If things need to be measurable, they are measurable. Okay. So the main thing is kind of a standardized notion of what learning is. And finally, for those who are already familiar with everything, familiar with statistical learning, I'm going to point out geometric phenomena in learning. Okay. Okay. So this is kind of a high-level cartoon picture that I draw in 5 minutes of statistical learning, right? So, so there is, let's start at the top left corner. The thing that we want to study, the thing that we as a humans or as an AI agent is interested in is something called a data generating process. This a data generating process, right? And here's first piece of notation. We are going to give it the symbol Q of X, and it's a probability density, a data generating distribution where you can sample from. Okay, so we don't have access to this, right? If you see Q, the true distribution appearing on screen, that's when you know that this is a theoretical discussion and quantities are theoretical quantities, right? But we do have access to the training data it generates. So it generates a set of n training data. So little n is going to be our number of our data set size, our training data set size, and d sub n is going to be our notation for the set of training data. And we usually do have the IID assumption, meaning, right, so capital X being an element of this training set are all sampled independently from the same distribution from this data generating process. So this is the IID assumption, and I'm going to use this assumption throughout. Okay. All right. So training data could be, say, the MNIST data, text data for GPT-4, or more mundane point cloud data. Or you could even think about things like experiments. So you do an experiment, the data generating process is physics, is nature, or if we live in a simulation, is whatever the simulation is. So you could think about or the positions of planets as you observe them is a data generating process. Okay. Okay. So then the next piece of the puzzle is someone, humans or future AI, would come out with a model, and P P of X, P of X, given W, that's our notation for a model. And what that means is that we are, and by model, we always means a parameterized model. That means that we have a parameter space, let's call that capital W. Think of this as a subset of R to the D. So it's a D-dimensional parameter space. And each point corresponds to a different distribution. So this is P of X at W. And a different point might represent a different distribution, or they might not. There might be an entire set that corresponds to the same distribution, etc. Okay, right. So think about, for example, if your data generating process is planetary positions around the sun, your model could be the Newtonian model or general relativity. Okay, I'm sort of taking a broad stroke analogy here. So a model is a parameterized space of distributions for us. Okay, so just to clarify, sometimes people in machine learning would mean model to be to gesture as something more complex, including the training algorithms and things like that. For us, model is a parameterized space of distribution, parameterized space of hypothesis. Okay, then on this space, on this parameter space, you can put on it a prior. We're going to touch on Bayesian learning later, so I'm just setting this up. Prior is just a probability density on the space of parameters on W, on capital W. Okay, so with all this ingredient, a learning machine is something that takes these ingredients, so including the model, a set of training data, a fixed set of training data, maybe some other things, for example, the prior, and maybe a different idea of loss function. You might include regularization terms in there. And the learning machine takes all this as ingredient and run an algorithm, crunch all that, and output something, output the train distribution, output the learned distribution, right? So in a more mathematical way of saying that would be a learning machine is an effectively computable, measurable function that takes in data and output another distribution. So this is kind of a formulation that is that might be general enough to include, for example, neural network training that you train with an SGD. You take in data. You have a model that is just the space of we have a fixed architecture neural network. The model is that neural network with its space of weights. You train and then you get an output network. But the output network is not a distribution. You can think of that as a delta distribution centered around at the trained weight. Okay, now we have take data, gotten a learned distribution. The statistical learning theory starts when you take that, you analyze its performance. By that we mean, how good is this learned distribution approximating the things that we want to approximate, which is nature, the data generating process. So we want a performance measure that tells us whether our p hat, sorry, the learned distribution is p hat. This p hat of x is any good compared to the true data generating process. So we want kind of a distance measure between q and p hat. And in SLT, the difference measure between the truth and the learned is the KL divergence. So it's defined as, so DKL from the true distribution to the learned distribution is defined as using this formula. Okay, to give a little bit of intuition, for those who are not familiar, the KL divergence is the amount of information you will lose if you don't have access to Q, but you have access to P instead. It's not symmetric, so we are measuring P against Q. Q is the thing that we're measuring against. If you swap the places, this is not a proper metric, but it is nonetheless it's a divergence, which can be you can derive a metric on the information manifold from that. Yep. So we'll go to concrete example in a moment. Okay. All right. So I've just dumped a ton of notation on you, right? And so I'm hoping that there will be some learning by osmosis here, right? I will go through for the next few minutes. We'll go through some different examples and just hoping that repeating this notation for 5 or 6 times would sorry, did you say, oh, Tia? Thank you. There's a minus sign there. Good catch. Okay. That's a very fast osmosis there. Okay. So literal statistics 101 example, a coin toss. This is I don't mean this to be overly simple, but I want an example that is simple enough that you don't need to think about the example, but just concentrate on the notation and the learning phenomena here. Okay, so coin toss, right? So the data generating distribution, okay, for coin toss, the nature, the natural process that's generating this observation is Q, and in this case, it is with probability W naught. Okay, W is W naught being an element of 0, 1. Real number between 0, 1. With probability W naught, it will come out heads, and with probability 1 minus W naught, it will comes out tail. Right. So data set dn. So you get n observation of this. So there will be heads, tail, heads, heads, tail, n of those. Okay. The model that we are going to use is of the same form, right? It's a parameterized family. So you get, so your capital W, your parameter space is equal to the unit interval. So there. And every point here represent a Bernoulli distribution. So it's W, if you are at W, then your probability, you hypothesize that the probability of observing heads is W, and 1 minus W for tails. Okay, so the negative log likelihood, the Ln that we are talking about, let's just write down what that is. That is equal to, right? So it's sum. So it's an average over the data. So data runs from I to little n. So there's n number of data, and it's the log likelihood evaluated at the data point. So it's the log likelihood is a function of the parameter. Okay, and it's negative log likelihood. Okay, so this is going to be kind of the main quantity we are that tells us about that capture the information how these distributions are arranged on the parameter space, and how the geometry of the model influences this function. When we talk about singularities, it's going to be related to the singularity of this function. In fact, this quantity is stochastic because it depends on the data. So these are the observation heads and tail. But there is a non-stochastic version of this, which is if you take the data average of W. Right. So if you see 1 on n, sum over 1 on n, replace that with average over Q of and there's a negative. Okay, so that's the that's if so. There's two ways to think about that. Think about this, which is if you take in the infinite data limit, then by law of large number, this will for point-wise for each W, Ln will converge to L. Or if you take the expectation of Ln with respect to the data with respect to the independent Xi, you will get this quantity. And this is kind of the main non-stochastic quantity that we're going to look at. Okay, now we're going to look at an example learning machine. Okay, so I'm going to use again a very simple learning machine example, which is the maximum likelihood estimator. So you get we have this Ln of W, which tells us how the lower Ln of W, the more likely it is that the distribution at W generates the data we observe. Which means if you want a p-hat, that could as closely reproduce the data that you are observing, you might want to just minimize Ln of W. And that's the main idea. So assuming that your likelihood function is differentiable, and which it is in this case, if you just do the obvious minimization, you get, don't have the note, so I'm doing this live. There is a, okay. So this is a sum over P of Xi W. And there are two types of terms in here, the terms that have Xi equal to heads and terms that have Xi equal to tails. So so there are 1 on n over some over h amount of terms that where x is equal to heads, which give negative log of W for those terms, plus that T be the number of tails in the data set, which give which happens. So you get so setting this equal to 0. You get that equation to solve. Okay, there is a good chance that I'm doing this wrong live, but the upshot is that the MLE W hat MLE. Sorry, I'm upstairs now. The point that solved this equation is equal to the number of heads divided by n, which is the frequency of heads. So this is to no surprise to anyone who have seen this example probably 10 times. So the probability of observing heads is just the frequency of heads, and which is also equal to 1 minus the frequency of tails. Okay, so we have got the estimator, which is our estimate of the parameter that minimizes our negative log likelihood. Because negative log likelihood is a mouthful, I'm going to start referring to it as energy in preparation to Jesse's physics lecture. So this is a parameter that minimizes energy, and once we got that, we are going to construct from this the coin toss MLE machine. So this is a learning machine that takes in. So this coin toss learning machine takes in the n, computes W hat MLE from that, which is just an algorithm that looks at the data set and count the number of heads, and then once it computes the MLE parameter, just output the MLE distribution, which is just the model at MLE. Okay, so this learning machine is a learning machine that counts the number of heads, and then the next time you ask it what is the probability of observing heads, it's just going to tell you the MLE probability, just the frequency of past observed heads. Now, statistical learning theory kicks in. Now that we have a learning machine, we can ask the question, how well does it do? And in this case, which is almost certainly not the case for any other non-toy example, we can actually compute the distribution of this MLE, right? We know exactly how this MLE will behave. Okay, I said distribution of the MLE estimator, the maximum likelihood estimator. And the reason I say that is the reason it has a distribution is because it is a stochastic, it is a random variable. It is random. What does it be? Why is it random? It depends on the data, which is random, right? You go out there, ask this natural process to give you another set of n example, you will probably get a different MLE estimator. So it is random, and hence it has a distribution. It is a random variable. Okay, so we can ask, what is the probability of this MLE computed this way equal to a certain value? Okay, what is the space of values? Well, MLE is computed as h on n. So the values is just taking, it's just going from 0 on n, 1 on n, 2 on n, all the way up to n on n. Okay. So we can ask the question, what is the probability that W hat is equal to h on n? Well, how do we actually compute this? Here is where this becomes a theoretical discussion, right? If we know, excuse me, if we know that the true rate of observing heads is W naught, right? This is where so recall that the true distribution has the opinion that the probability of heads is W naught. Then we can compute the distribution of W hat, right? Okay, so what is the probability of this algorithm output h on n? Well, it's a probability of, if you have n toss of coins, you observe h of them being heads. And that's just a very basic binomial distributions, right? So, the probability of heads is W naught according to the true distribution. We want to have h of them being heads, so that event needs to happen h time independently, and then the rest of them have to be equal to tails, and n little n is equal to h plus t. H being the number of heads and T being the number of tails. So this is T, and order doesn't matter. So here's where we just need n choose H of them to be that. So this is the binomial distribution. So W head is binomially distributed. Really, it is shouldn't write that. That is false. H is binomially distributed, and that means H on n therefore has the same distribution. Okay. Now that we have complete information about the behavior of, give me a new data set, I can tell you what my learning machine will do. We can ask a few questions. What is the expected prediction, right? What is the expected, this is asking, what is expected value of W hat? So if I repeat this experiment a gazillion time, and then plot this distribution, plot the distribution of W hat, what would I see? Well, if you compute that, this is so 0 to n of H on n, and then the binomial to the n minus H. So you can do this sum either observing that the binomial is sum of independent Bernoulli, and you will see that this is just W naught. Okay, this is actually really good news. What that means is that if you want to get to the true parameter, the true if you want to know Q of X, you can repeat this experiment a number of times, and then your estimate of this is going to take the average. You will get the true distribution, right? This is known as consistency. Sorry, this is known as unbiased estimator. So MLE is an unbiased estimator, right? The mean is equal to the to the parameter that generates the data. Okay. Next, you can also ask. I should have used the. Next, you can also ask. Okay, sure. If I repeat this experiment, the mean will eventually give me the true parameter. But how many repetitions do I need to get that? So this is a question of the variance of this prediction. So we know that the MLE is a random variable. It will fluctuate, and then the good news is that the fluctuation is centered around the true mean. But how far is it from the true value? Well, this is we can ask the variance. The variance of W hat. Okay, you go through similar calculation using sort of properties of binomial distribution. You will get it is equal to this number. So I'm using the fact that the variance of a binom NP is equal to NP1 minus P. Okay. Sorry, missing a. Yep, thank you. So if X stat, then variance of X is equal to that. Okay, so this is another piece of good news. It says that if you you get quite a bit of bang for your extra data point buck. So if you want your prediction to be really, really close to the true, if you want to recover the true parameter, you can just make a ton of observation of this data generating process, right? Because it says that
W naught between
it's
0
really,
and
really
1?
large, then the variance, the fluctuation from the mean is very, very small. And it decays like 1 on n. In fact, we also have another piece of property of the binomial distribution, which is that the binomial NP around the mean, you can approximate that, so converge in distribution to normal centered at the mean and with the variance with the variance of the binomial distribution. So as n goes to infinity. Right. Okay, so this is for binomial NP. So so this for us, this means that the MLE distribution, which is h on n, eventually converge in distribution to normal with the mean that we calculated before, which is the true parameter with the variance that we computed before. Okay, so what does that look like? It looks like that. Okay, quite a lot of plots. Let me break this down one by one. So so going from top to bottom, you will see that n, little n, sorry, I used capital N in the plot. So the data set is increasing, n increasing. And going from left to right, W naught is going from W naught is increasing towards 0.5. Okay, so let's look at the top to bottom first. Let's look at the last column. So here, the true data generating distribution is a fair coin, right? The probability of seeing heads and tails are equal. And from there, we have the variance. So let's remind us a little bit again, the variance of is that. So as n increases, so going from 10 at the top to 100 at the bottom, the variance, the distribution becomes sharper. And secondly, as n increase at 100, the histogram is very much well approximated by the density, the red the red curve that is the normal density with the proper mean and variance. And you can see that the histogram and the normal distribution pretty much match. It's not so when your data set is only at 10, but in this case, it's still pretty good. Okay, however, this is our first hint where geometry already play a role in this very, very simple example. If you go to the left, if you look, let's look at the third row. Let's look at this row. And then if you go from right to left, you can see that yes, in this one at n equal to 50, the normal distribution is already a very good approximation of the distribution that we want, and it is centered at the correct place, right? But if the data generating distribution is not so fair a coin, the normal approximation start to get worse and worse as you approach the. Okay, this is not quite the singularity that we are talking about, but as you approach the boundary point. So the geometry at the boundary changes there, right? And you can so you can see that if n is small, this is even worse. If n is small, you have the variance being large. It means that the correct normal distribution to approximate your histogram is very spread out. But if your distribution is very much at the boundary, well, the normal distribution is symmetric. The tail is still fat for low n, and our true histogram has no probability mass left of 0. So something went wrong there, right? And it's only when you, so for W not really close to the boundary, this is at 0.01, you need n to be truly huge before your normal distribution is so sharp that it doesn't care about the boundary, right? So kind of remember this kind of effect. There are more dramatic version of geometric effects later on. Okay, so there's further things we can ask of a learning machine. So we can ask, how difficult is it to narrow down to the true W naught, right? This is the effect of geometry that we're talking about. We have a very clear formula. We have an answer in this case, which is how hard is it to narrow down to W naught? Well, it's the variance. The variance is decaying like 1 on n, but the variance doesn't only depends on 1 on n. It also depends on where W naught is, right? How hard is it to narrow down to the thing that you want to learn? Depends on the geometry near the true parameter. Okay, and I want to introduce something that quantifies that in at least in this case, right? So this is something called, yeah. If there's any question, put it in chat and I'll pause for question soon. You can interrupt me too. And please do if there is anything not clear. Okay, so there's this quantity called a Fisher information matrix. Let's go through the formula first. So if I have a model, again, model is a parameterized family of distribution. So imagine this is your parameter space. This is W. It represents the distribution P of X at W. The Fisher information matrix, well, it's a matrix at that point, I of W. It's a matrix with whose entries, whose ijth entry are the following. It is this is the log likelihood, the log likelihood of model. Actually, let's just be consistent and say that is those are negative log likelihood, and the negative cancel out. And we are looking at the derivative of the log likelihood with respect to the ith and jth parameter. Okay, perhaps a much more intuitive version of this would be this is actually equal to this is so under certain regularity assumption. Okay, I should be wary of that word. Under certain sort of nice differentiability assumption, for example, if the log likelihood is smooth, then this is equal to the partial so the mixed partial, order doesn't matter, of the log likelihood. Okay, so that's the term. Apology for that. I'm going to write it. I'm going to write over the. So that's the quantity that we are going to take average of. So Okay, so if you look at this expression, so this is I of W, the ij element of this. This is the expectation of the Hessian, well, the entry of the Hessian, the ISJ entry of the Hessian, right? So in a sense, it is quantifying the curvature of. Okay, let's be precise. So this expectation is taken using the distribution at P, the model at W. So this is saying, were your data, if your data is generated from the distribution at W, so if W that is the actual data generating process, how what is the expected curvature of your log likelihood at that point? So if you think about if you are at W, and then if you look at if you look at a slightly different parameter, you will get a slightly different distribution. And this is quantizing how hard it is to distinguish the distribution at W with the distribution around it, right? So the more sharply curved it is, the more sharply curved the log likelihood is at W. Tiny steps away from from W will produce a vastly different distribution. That means if the data is generated by the distribution at W, if your learning machine is saying that your parameter, the learn parameter is slightly away from the true one, then the likelihood will actually be very different. It's noticeably different because it has changed a lot, right? This is related to this learnability, right? So the more sharply curved you are at the place in the parameter space, the easier it is to distinguish the things that you want to learn from nearby things. Okay, for our coin toss model, there is a surprising thing, which is if you just calculate this. So this is a discrete model, so integral becomes sum. If you calculate the Fisher information matrix, this is a one-dimensional model, so there's no matrix here. It's just a scalar. You get this quantity, right? The Fisher information matrix at W is 1 over W times 1 minus W. You might be that might be a little bit familiar, which is that this is the variance. The variance, remember, was equal to which means that it is equal to 1 over n times the Fisher information matrix at the data generating distribution. So this is kind of a direct link to if my explanation of what the Fisher information matrix is not intuitive enough, is unclear, then this is kind of an illustration of its direct link. The Fisher information matrix for this model is directly related to the variance in this way. So the smaller the Fisher information matrix is, the larger its variance, right? So the larger the Fisher information matrix is, the more sharply curved in the parameter space it is, means that in this case, the variance is smaller. So for example, when W is equal to 0.5, which means that the variance decays even at low end, the variance is already very small, meaning that the true W naught is easier to locate. Okay. In fact, this is a very fortuitous situation for this extremely simple model, which is that MLE for coin toss. Let me just say that, which is that this coin toss MLE machine is efficient. What that means is that there is this theorem known as Cramer-Rao inequality, which says that if you are using an unbiased estimator, which our MLE is, remember, because the expectation of our MLE is equal to the actual parameter that generates the data. So the Cramer-Rao theorem says that if you have this property that whatever actual parameter generates your data, your procedure, your learning machine can actually it is equal to the true parameter in expectation, then your variance cannot be larger than the quantity we just stated. So for any other unbiased estimator, the variance of that estimator is at least the variance of the MLE estimator, which is equal to this lower bound quantity. Okay. In fact, this is going to be a general feature of the regular side of things. It's going to be a general feature of regular models, and regular as opposed to singular in SLT, the S in SLT, right? This is going to be a surprising state of affair in the world of machine learning. This is an assumption. This is an assumption that is that there is frequently present. The fact that you have unbiasedness and things like that. Okay, we're going to summarize that in a moment. Okay, this just to have a little bit of variety. This is just quickly go through another regular model, another model where things are nice. So this is just a simple 2D Gaussian model. Okay, that's a little bit of variation on the theme on the notation. Instead of writing Q of X, I'm going to write Q of XY, and that just means that my X is now a tuple, X and Y. Right. So Q of XY, the true distribution on XY is given by this two-dimensional Gaussian with mean A0 and A0 for X and B0. So the mean of this is A0, B0. Okay, so the data generated, what does it look like? Well, there's n data set, and each one of them is a sample drawn from the true distribution. In this case, it's a distribution on tuples, so it looks like tuples of numbers. Okay, there's n tuples, n2 tuples in this set. So what is our model? Let's again look at a model that is of the same form. It's also a two-dimensional Gaussian, parameterized by A and B. So our parameter AB, parameter W is equal to the tuple AB in, say, O of R2. Yes. Yeah.
Yeah.
The matrix being greater than or equal to. Thank you. That's part of my notes. I forgot. So a matrix, if I have a matrix A and a matrix B, A is less than or equal to B, if and only if A minus B is okay, I should have is negative.
B minus A.
Yeah, I just sorry. Okay, let me change that. Good point. Okay, then if only if B minus A is positive semi-definite, So positive semi-definite means that in if it is a square matrix in so X is okay. You use X. C is positive semi-definite if X transpose CX is always greater than or equal to 0 for all vectors X. Okay. Or if it is diagonalizable, all the eigenvalues are non-negative. Yes.
Didn't quite catch this. Do we know when it's an equality? Is this true for all regular models or no?
No, it is not true for all regular model. This is kind of a very singular event. Yeah, this is actually so. Actually, for regular model, it is asymptotically efficient. It means that eventually the variance you replace equality with asymptotic equivalence.
Right. Okay. So it's sort of close.
Yeah, close to being true-ish. Yeah. Again, with some regularity condition on top of being a regular model. Okay, so for this 2D Gaussian model, our negative log likelihood, our energy function is looks like that, and I just wish to mention that while this is sum of squares, so this is the mean square error, or in physics terms, this is the energy function of a simple harmonic oscillator. So intersection of fields here. Okay, so what does this energy function looks like? If you plot, this is a 2D energy function that depends on A and B. So W is equal to AP, remember? Those blobs, okay, let's focus on one plot here. So that blob, by that blob, I mean the contour plot is the contour plot of L and of W. I didn't label my axes. X-axis is A, Y-axis is the parameter B. Okay, and the top row has n equal to 5. It means that the data set has 5 points in it. Why do I plot them 4 times? Because those are 4 different data sets of 5 points. And you notice that this log likelihood, because it depends on data, is fluctuating. It is a random variable. It depends on the random data set. So this entire function, so previously we were talking about the MLE of the coin toss. It is a random variable. It is a number that fluctuates. Here we have an entire function. Well, the log likelihood of the coin toss model is also fluctuating like this. This is just kind of a more visceral visualization that the entire function is fluctuating, is changing around. Still, this is a regular model. The fluctuation is kind of captured by a single number. Where is the center, right? So just very much like the coin toss case, a single number, the shape is changing, but that number is sort of the main thing that is fluctuating for the entire function. Yes.
Right. So what is the circle thing?
So
exactly?
The circle thing is a contour plot of this function. Okay. So okay, little n is equal to 5. Go and ask this natural process to give you 5 observations. Plug those 5 observations, those 5 x and y's into this formula. You get a function of A and B. So no, that is not correct. Okay, so then let me drill down on this. Okay, so the center of that blob looks like it is the brightest. So it is as a surface plot that this is highest. That is saying that according to this 5 data points, this x1, y1, ... x5, y5, that parameter, this parameter has the highest likelihood. That does not mean that it is the true parameter, right? Because, well, there's only one true parameter, and that blob is fluctuating, so it can't be the true parameter, right? Okay, the actual true parameter is this little diamond here. Sorry, you meant to the center of the plot. Sorry, right? The center of the plot here, the true parameter is fixed at 0.5 and 0.5. Yeah.
Yeah, maybe we're gonna explain this, but what is the little red dots in the little black, like little path?
Yes. Okay.
Mice.
Yep. I'm going to explain that. Let's clear the plot.
Ooh.
Okay. So so point number one, the energy function depends on data, right? It's a random variable. Okay. Okay. From this energy function, we can construct various different learning machine from it. One learning machine that we have seen is the maximum likelihood learning machine, which is you look at this energy function and find its lowest point, or you look at this likelihood function and find its highest point. For that, these are the MLE, right? You just look at this contour and find the brightest point. Okay, but that is just one learning machine. You can use other learning machines. For example, SGD, right? So the black path is actually SGD path. So I randomly initialize at somewhere, and then ask, by SGD I mean stochastic gradient descent. It's for those of you who are unfamiliar, it means that I randomly initiate at some point, look at a subset of the data, and compute the gradient of this energy function of this log likelihood, and then step in that direction a little bit, and then do that for, I think I take 20 steps in this case. Okay. Yeah, I think I take batch size equal to 2 in this plot, right? Out of 5. Yes. This is not neural networks here. Okay. I can't even visualize a neural network. Okay. Okay. And the red path is yet another learning machine. So the black path, so MLE will give you a point. If you plug that point back in your model, you get a p hat, you get a learned distribution. SGD will give you another point. You run it for a certain number of time. So there's a hyperparameter there, just what's your stopping criterion. There's a number of hyperparameter. That will give you another point. So so there is W hat MLE, there is W hat SGD, and then there's the red path, which is W hat SGD plus momentum. So it's just another stochastic optimization algorithm. The point here is that there are multiple different learning methods that will give you, in this case, different point estimations. They're all different. They all have their own they all depends on data, because ln itself depends on data. So they're all random variables, and they are all effectively computable because, well, I just described the algorithm. Yes.
So yeah, I actually have a question. So when you defined a learning machine, I think it was like a function of the data and your prior, and I think one other thing. So SGD, as the name suggests, is stochastic, even given the data. So is it allowed to be a stochastic function, or we can consider like the random seeds of SGD to be part of the training data? Or
yeah, so so you can so the learning machine is an algorithm. So right. That algorithm, you can have the algorithm depends on as many hyperparameters as you want.
Yeah.
Okay. So here SGD, I'm using it to gesture at kind of a family of things, and of which I've taken one of them. So this is SGD with batch size of 2, with 20 stepping 20 times, with a certain learning rate, etc. Right. So So I'm not claiming that I'm giving a formal definition here. I'm just saying that it's an algorithm that produce. So as you said, if I change the learning rate, if I change the initialization, you can argue that that is a different learning machine.
Sorry, what I mean is that like SGD, stochastic, because it depends on the batch work.
Yeah,
right?
yeah.
And so is the idea that we'll just like imagine fixing that as a hyperparameter?
Sure. Okay. Yeah, yeah. You can say that put the random seed as part of the hyperparameter in your algorithm. Yeah. Okay. Right. Okay. So so from top to bottom, again, we see that if we increase n, there is the likelihood sort of concentrate more. So and concentrate towards the true parameter. Sorry, that little diamond is probably a little bit hard to see, right? So again, we have all the similar phenomenon we observed before, which is things concentrate as n increases and it fluctuates around. Okay, summarizing, these are again the recurring notation. So models, one model, one family of distribution can be used with different training algorithm that give you different learning machines. Predictions depends on data. Therefore, predictions are random variables. Therefore, the predictions that your machine output, if you want to measure their performance, the performance measure themselves, your error, etc., are random variables as well. So this is where the statistics of statistical learning comes in. We need to study the statistics of these either the performance measure or MLE, etc. Okay, so things are not going to be as nice starting from now. In all preceding models, we have the following properties that makes things nice. The first property is what we call identifiability. So this is a property. So okay, these are properties of models, right? A model P, X, W is identifiable if and only if the map that sends parameter to distribution is injective. That means that you can conflate distribution with parameter. Each parameter identify a unique model. There is no two parameter that points to the same distribution. Okay, that's identifiability. And second, the Fisher information matrix. So we were talking about the variance of our estimator being 1 over the Fisher information matrix, or it was greater than or equal to and asymptotically converging to that value. We're talking about 1 over that. So 1 over the matrix. We're talking about the inverse of the matrix. That was a scalar, so I was writing that. So in general, it's that. So in all preceding discussion, we require that the Fisher information matrix is invertible. And because the Fisher information matrix is always positive, is always by definition positive semi-definite, that is equivalent to it saying that we require that the Fisher information matrix being positive definite is equivalent to saying that it is invertible, or the determinant is non-zero. Okay, so these are two sort of characterizing properties of something we will call a regular model. I'll give this definition later. And these actually also sort of implies that the L, the average version of the log likelihood, negative log likelihood, has a unique global minimum. Okay, so in preceding examples, there is a true parameter. Well, the log likelihood is definitely smallest at that true parameter. And since there is no other parameter that parameterize the same distribution, in that case, in this case, the true distribution, then that point, the true parameter is a unique global minimum. Okay. And with these properties, as well as some other regularity conditions like smoothness of the log likelihood, etc. This model enjoys a few properties that we have seen in our previous two examples, which is they are consistent, meaning that if you take n large enough, if your data set gets large enough, the parameter that you learn is the actual parameter that generates the data. It is asymptotically normal. Eventually, a normal distribution would approximate the distribution that you want, and it achieves the difficulty of locating the true parameter is as efficient, is as close to theoretical the theoretical possibility as possible, which is this n times Fisher information matrix inverted. Asymptotic consistency means that the parameter that you let's look at the asymptotic consistency. The question was what is asymptotic consistency? It means that your likelihood eventually just becomes is at the true parameter. It means that your learning machine, at least the part that estimates the parameter, if you take large enough data set, will be arbitrarily close to the true parameter.
So this is very similar to
yes, it is similar to that, except the bias unbiased is related to the expectation of the estimator. It is related in certain sense. For example, the law of large number says that you eventually converge to your expectation. Okay, yeah.
So one nice property that I noticed of the previous models is that they were in the realizable state. So like the real probability distribution was one of your options.
Yep.
Are we going to be assuming that continuing, or is that one of these nice properties that's going to go away?
Okay, I'll have a slide about that later on, but the answer to your question is we don't need the realizability assumption. It can be relaxed very substantially for singular learning theory. But throughout this series, I'm going to assume it because that's a technical condition. I will gesture at how to relax that later.
Great.
Okay. Okay. Here's another log likelihood, and it looks nothing like a blob, like a circular blob, right? Okay, and going down again, n is starting to get really large. N is at 200. This is a two-dimensional model, and with n equal to 200. And it is no way close to looking like a normal distribution. So I think we expect the asymptotic normality to be out the window for this model. I haven't said what the model is. I'm just letting you see that the log likelihood is nothing like a circular blob. Okay, okay, let me put a dividing line here. The true distribution, the true parameter is the same for everything on the left. So these ones. So let's look at the top two. So these are so I sample n5 data point from this true parameter and plot the log likelihood. One of those samples makes the log likelihood looks like this, and the other 5 data points makes the likelihood looks like the one on the second plot. Yes, A is on the y-axis. A is 0. So the true parameter is on the y-axis. Okay. Right.
So if A is 0, Y is 0, is beta?
sorry, I haven't even tell you what the parameters are. Okay, let me just answer that question. The true distribution is this is a regression model where the output parameter is related to the input by a tan h bx. Okay, x is the input and y is the output. And this is not a statistical model because there's no stochasticity. The idea is that there is some noise and the noise is Gaussian. It means that the model looks like this. It means that y minus a tan h dx is Gaussian, is a random variable that distributed like Gaussian 0, 1. Okay, so if the true parameter is a naught b naught equal to 0, I'm going to speed up 0.5, as it is the case on the left two plots. Okay, what does that mean? It means that so if a is 0, if a is equal to 0, then it doesn't matter what b is. This whole term is 0, right? So it means that everywhere on the, so just now I was saying a equal to 0, everywhere on the y-axis parameterize the same distribution. Okay, so this is identifiability have been violated. We don't have one-to-one correspondence between parameter and distribution. So looking at this formula again, if b is equal to 0, tan h is 0 at 0, and doesn't matter what a is, the whole thing is 0. So everywhere on the b equal to 0 line is the same distribution. Okay, right. So the distribution is the same whenever a b equal to 0. Okay, so if I were to generate data from true parameter anywhere on that is on this axis, then the set of true parameter, before it was just one parameter, that w naught denote the set of true parameter. Before, if you have identifiability, this capital W naught is just equal to little w naught. It's just that set. But now, w naught is this whole axis, the x and y axis, and there's infinite number of points for one. It's not just a singleton point, and it is defined by an algebraic equation. And this algebraic equation defines an algebraic variety. It defines a set of points arranged so that there is a singularity. Okay, so this is an example of a singular model. If you go and calculate the Fisher information matrix, it is not positive definite on this axis. The determinant is 0 on that axis. It doesn't mean that the curvature is 0. It means that the curvature is undefined there. Yeah, I just yeah, yes. Yeah, I was using that term too loosely, and I stopped myself there. Right. Okay. So so another thing to point out is that the fluctuation before the fluctuation where in regular model where your fluctuation is kind of characterized by a very small number of numbers, the position and so on, is no longer true here. The fluctuation seems to be kind of a whole seems to be kind of a changing the entire characteristic of the Ln function here. Okay, it might have different, the level sets have different topology and so on. Okay, yes. Can you repeat the first part?
The model is statistically singular, regardless of the singularity.
Yes.
Farther to me.
Yeah, let me give the definition right now. Okay, a statistical model is regular if it is identifiable, meaning one-to-one correspondence between parameter and distribution, and it has everywhere positive definite Fisher information matrix. So the answer to that, okay, and it is singular. It is strictly singular if it is not regular. Okay, and there is this convention that we are kind of using, which is singular model refer to both strictly singular and regular model. But I think I'm just going to use singular for actual strictly singular. So to the answer to that question is yes. Whether or not a model is singular is a property of the model, not of whether or not what data what data it is learning, right? Regardless of what the data is learning. If you are not identifiable, then you are singular. If somewhere in your parameter space your Fisher information matrix has determinant 0, you are singular. Okay.
This question. It's not singular because it's a true parameter.
Yes. Yes. Okay. I get it now. So yes, we are using singular in multiple contexts here. There is singular in this sense. There is, and I was talking about singularity in the sense of singularity of a algebraic variety. So if you have a level set, if your true the set of true parameter is singular in the sense of being singular as an algebraic variety, then your model is certainly singular. Okay, it doesn't. Okay, the converse is not true. It means that if your model is singular, you may not have a singular true parameter set. For example, these ones. So this one is where the true parameter is 1, 1. It's a way. So I claim that the only set where the Fisher information matrix for this model has vanishing determinant is the axes themselves, the x and y axes. And now our true parameter is away from the axes, right? So W naught in the case of these right plots consists of 2 points, which is the point W0 itself and negative W0 somewhere here, because 10H A 10HB have this Z2 symmetry. So it's 2 points. That is not a singular algebraic variety. It is still not identifiable. There's 2 parameters that parameterize the same thing. Okay, and here is sort of recalling back to what Dan was saying before, which is even though the chances of your true parameter landing on this measure 0 set, that this measure 0 set of determinant of Fisher information matrix being 0 is unlikely. Still, this is at n equal to 200 for a 2-dimensional model that looks nothing like a normal distribution. If you want to look, you need to. I think my computer can't handle plotting the contour plot if I increase n high enough that you can actually see it as a blob, as a normal blob. For this model, you need to increase n so much that it's so concentrated that before the effects of geometry at the tail end sort of goes away, right?
Oh, great.
Yep. Yes, exactly. So this is we do have asymptotic normality, except that's not true because normal means that you only have single mode. But modular, like if you just if your parameter space is only the upper half plane, then you are asymptotic normal, right? Eventually, you will concentrate convergent distribution centered around the true parameter.
Asymptotic mixed normal something.
Yeah.
Okay.
Yeah. Okay. Okay, I'm going to. Okay. Okay, I'm going to introduce the some of the Bayesian stuff with apology to Dan, because we probably need to talk about the Bayesian stuff in SLT High next lecture. Right. It's just a little bit of preview of next time. Our goal is to get to the free energy formula, and there are two ingredients in my mind, there is two ingredients to SLT. There is the geometry part, and then there is the statistic, the stochastic part. Next lecture, we are going to focus on the geometry part. So the how do we handle situation when your true parameter set has an algebraic singularity? What happens to the various quantities we want to learn in those cases? Purely, so instead of focusing on Ln, which is a stochastic quantity, we focus on its average, just to remove the effects of stochasticity for now, and before we add it back for the full exposition. Okay. All right, I'll pause for question. Thank you. Any question?
Alex, for every statistical model, is there a regular statistical model parameterizing the same family of probabilities? Can we limit?
Yeah, right. So the question is, so if we get a model, we look at its image. So model is a family of distribution. Forget the fact that it is parameterized. Just look at the set of distribution. Is there a way to parameterize it so that in the parameter space we don't have the singularities that we talk about? I don't know of a general if there's a general way of doing that. I do know that you can't just inspect the parameters and then you can't just inspect the parameters and make an algebraic transformation of. So if your starting parameter is W, so W is our starting parameter, you can't take a algebraic transformation. You can't have a G. You can't have a U equal to G of W, so that in the U coordinates your model is regular. That is not possible in general. There are toy models where that is where you can do that.
Something related on shrinking.
Oh, you mean the one cutting down number? Yeah.
Yeah.
I mean, I think it's a formal question whether or not it's possible, but conceptually, come back to the question that was asked during my talk about sort of the computational complexity of things involved. It could certainly be formally possible, but at the same time, like actually irrelevant, because it's far more desirable computationally to operate in the thing with the singular parameterization than the regular parameterization, even if it were possible to do that.
Do we know why? Like, yeah, why?
Why? That's Matt's talk. Yes, I mean, Matt's talk says that, well, okay, that's part of the answer. Yeah, I think I can't give a short answer to that question, nor do I really understand the answer. Maybe, I mean, there are platitudes you can say about optimization in high dimensions being easier or something, but I think this is a deep question. I'll have to think about it, unless you have an answer.
I don't have an answer in that full generality, but again, as a preview of next lecture, I will show a situation in which there is in which there is the redundancy is such that the model doesn't depend on an entire set of parameters, for example. And we will show that you can quotient those parameters out, and then you will get an identifiable model, but there are still consequences to that. And I will show increasingly more sophisticated example of that. Hopefully, you can see the difficulty in the full generality, in the fully general case. Yes.
So we talked about Q of X.
Yeah.
And you hinted at regression.
Yeah.
Does it transfer fully to all kinds of probability distribution modeling?
So I can confidently say that all most supervised learning situation, you can translate that to the framework that we were talking about. So for example, instead of modeling, so your output, your learned distribution will be a probability of y given x for a regression problem. So instead of y equal to f of x as your output, you have a probability for every x, you have a probability of y. If you can collapse it down to a single prediction by taking expectation, by looking at the mode or things like that. I understand that this is a theoretical discussion where we just throw around things like we just manipulate distribution as if they are easy things to manipulate. But this is theoretical discussion. We are using this to understand that. Yeah. Other questions?
Talked about KL divergence.
Yeah.
But which was
Deterministic?
Right.
Oh, right. Just L2 loss and the one reason that we are looking at KL divergence, just part of the reason is that it has nice properties when we talk about Bayesian inference, Bayesian learning later on. And if you are thinking about other loss, for example, in training neural networks, where you use L2 loss with regularization, I think Jesse will, in the physics talk, will look at examples, and we have there are, so as you can see just now, there are situations in which the using those laws is equivalent to using Gaussian. I'm going to flash a slide. So for example, the energy function is if your noise is a Gaussian, if you are doing regression and then your regression noise, your observation noise is Gaussian noise, then it is equivalent to having your energy function being a mean square loss. If you change the noise distribution to be exponential or Laplace distribution, you recover something like a mean absolute error, which is an L1 loss. Okay. Any other question? Okay. Thank you.